So we're going to start talking about some electrical components. The first one is capacitors. Capacitors have capacitance, and they're used for storing charge. This is a battery, and we've looked at this, these are sort of parallel plates, and so they might have some area A, but we're just going to look at them edge on and just talk about them a little bit for a minute here. So this has some battery, it has a voltage V, maybe 20 volts or 12 volts or something. And let's just pretend there's a switch here, and so I close the switch down, and so now I have a closed circuit, so-called a closed circuit. And what happens here is this is the positive end and this is the negative end. What a battery does is it's a pump, and so you can say it's moving positive side charges to this side. So it's grabbing positives off this side and sticking them on this side. Actually what it's done is it's grabbing electrons from this side and pumping them onto this side, but it's the same effect. For mathematical reasons, actually historical reasons, we pretend that positive charges are moving. What's really happening is negative charges are moving in the backward direction to where we say the positive charges are going. So when I throw the switch, charges start to move onto this plate, for example, like this, and I'm just reducing the number here a little bit. And so as charges move onto the plate, they go on kind of in pairs because I'm taking one off one side and putting it on the other side. And so you can see an electric field builds up between these two plates. And so it points from positive to negative. Electric field lines start on positive charges and end on negative charges, maybe like this. The charges will spread out so it'll be fairly uniform. And as this thing puts more and more charges on, the electric field gets stronger and stronger, because if you remember, the electric field is proportional to the density of the lines. And so the more charges that build up on these plates, the stronger the electric field. Right. And so I get a stronger and stronger electric field. That's what's happening in the plate as the battery is doing its thing. Eventually, the battery loses the ability to pull more charges on. So for example, if I'm going to stick another positive charge on here, now first of all, when I grab it from this side doesn't want to let it go because it's all negative and it's pulling back on that positive charge. And this side doesn't want to accept it because it's got a whole bunch of positive charges and I'm trying to stick one more on. So eventually the voltage on the battery limits how much charge I can put on these plates, and I'm just stuck there. And so there's an electric field E here. If the plates are a distance D apart, we know from our previous work that the voltage between the plates is just the electric field times the distance if the electric field is uniform. And so the voltage between the plates ultimately is the same as the voltage on the battery in this case, but this is, if I can measure the electric field, I can also multiply that by the distance and get the voltage. Notice that the electric field is directly proportional to the charge Q on the plates. That is to say, if I have Q in positive charges, this is going to be plus Q on top, and this is going to be minus Q on the top and the bottom. With a capacitor, it'll always have the same number on one side as the other. And so, because they go from one side to the other. And so, when a capacitor has plus Q on one side and minus Q on the other, we say, let me just write it this way. Has charge Q. Since the electric field lines start on positive charges and end on negative charges, the electric field strength is directly proportional to how many charges there are there. If there are twice as many charges, then the electric field is twice as big because there are twice as many lines in the same area. And so the electric field is directly proportional to the charge. And since the voltage is proportional to the electric field, it's the electric field multiplied by the distance. We can say the voltage on the capacitor is proportional to the charge. So if the voltage is proportional to the charge, then we can say the charge is directly proportional to the voltage. We can write that proportionality in either direction. So Anytime you have a proportionality, you can replace it with an equal sign, and so we're going to write this. We're going to change this proportionality to an equal sign, and we're going to say the proportionality constant, we're going to call it C. And so we get Q equals CV. The charge on the capacitor is proportional to the voltage. That is to say, the greater the voltage I put on here, the more charge I get. And it sort of makes sense because the battery has a bigger pump, and it can pump more charges through before it can't do that anymore. And so Q is equal to CV, and C is called the capacitance of the capacitor. And so capacitance is a quantity, is sort of how efficient your capacitor is at storing charge. If you have a really good capacitor, it can store a lot of charge at a small voltage, and so C is large. If C is really small, you can't store much charge for a given voltage. And so, as you might imagine, the capacitance of a capacitor kind of depends on things like its shape, its area, or how far apart the plates are and stuff like that. And so we'll get into that in a little bit. We can say the units of capacitance are, so if I solve for C, I get C equals Q over V. And so for the units in SI, that's coulombs over joules per coulomb. Well, coulombs over volts, which is coulombs over joules per coulomb. And so the capacitance is coulombs squared over joules, and this is called a farad. So the SI unit for capacitance is a farad, and that's a coulomb squared per joule. So in this section, we want to learn the capacitance of a parallel plate capacitor. Most capacitors can be treated as just parallel plates. And so I've got some battery, and it's charging up some capacitor. And I'm going to say the plates have area A. So separation D and charge Q. And now we know that the electric field between the plates, right, we already said that that's proportional to the charge on the plates, because the electric field is proportional to the line density, and so that's proportional to how many charges you have. But it's also inversely proportional to the area, because the more area I have, the more spread out my charges are. And so we can write this way. It turns out that you can turn that into an equals by putting a constant in there. But it turns out that the constant for that is 4 pi k, where this is the Coulomb constant, 9 times 10 to the 9th newton meter squared per Coulomb squared, Q over the area. And so this is the electric field between the plates of a capacitor. We've already said that the voltage on a capacitor is equal to the electric field times the distance between the plates. And so now we can say that's equal to 4 pi k Q over over area. Times the distance between the plates. But if you remember, we said V is equal to the electric potential is Q over C. Well, that's just equal to 4 pi k Q times D over the area. So if you just look at this piece, you can cancel the Q's and rearrange the equations, and you get capacitance is equal to the area over 4 pi k times the plate separation. we define this quantity called epsilon naught as 1 over 4 pi k. It just comes up a lot. By the way, it's equal to 8.85 times 10 to the minus 12th coulombs squared per Newton meter squared. The units are just 1 over what the Coulomb constant was, right? And then you have 1 over 4 pi k there. And so so you can write the capacitance is epsilon naught A over D. This, for a parallel plate capacitor, says its ability to hold charge, its capacitance, just depends on this constant times the area of the plate divided by the distance. In other words, the bigger the area, the more charge you can pack on there for a given voltage. And that sort of makes sense because the charges can spread out a little bit and get away from each other. Similarly, the smaller the plate separation, the more charges you can put on there. Well, that kind of makes sense too, because if I have a whole bunch of minus signs here and a whole bunch of plus signs up here, when I bring an extra positive charge on, it's repelled by these guys. But if the plates are really, really close together, it's also attracted by these guys. And so the fact that these guys are really close reduces the repulsion, and I can squeeze more charges on there. And so this at least is a sensible answer for the capacitance of a parallel plate capacitor, and it's the right answer. So in this problem it asks, what is the capacitance of a parallel plate capacitor with an area of 1.5 meters squared, or square meters, with a plate separation of 2/100ths of a millimeter, right? And so we just say the capacitance is epsilon naught A over D. That's 8.85 times 10 to the minus 12th Coulomb squared over Newton meter squared times the area, which is 1.5 meters squared, divided by the plate separation, which is 2 times 10 to the minus 5th meters, right? If I multiply all that out, what I get is 6.6 times 10 to the minus 12th Coulomb squared. So my meters squared and meter squareds cancel, and this still becomes a Newton meter, which is a joule. And so I get Coulomb squared per joule. It's not 6.6, it's 6.6 times 10 to the minus 7. And so that's 660 nanofarads, right? Nano is 10 to the minus 9. And so it's 660 nanofarads. So now we're going to take our capacitor that we just identified, and we're going to put a battery across it, right? And we're going to ask how much with, V equals 100 volts, what's the charge, right? And we know that Q is equal to C times the voltage. And so once it charges up, it might take it a little while, but once it charges up, then the charge it carries is 660 nanofarads times 100 volts, right, which is 6.6 times 10 to the minus 7. So a farad is a Coulomb squared per joule, and a volt is a joule per Coulomb. Right, so I cancel a joule and a Coulomb and a Coulomb. My answer comes out in coulombs, and that's good because that's what I was after. Right, and so it's 6.6 times 10 to the minus 5th coulombs, or 66 microcoulombs. this much charge is on there. So it turns out you can increase the capacitance of your capacitor by sticking what's called a dielectric inside. Here's the idea. So I have a capacitor here, and then I attach it to a battery, say. Right. And then I put a piece of rubber or some other non-conducting material inside my capacitor. Now, because it's non-conducting, the charges are still trapped to be on the plates. But what happens is if you look at the individual molecules inside the dielectric, so I'm just going to pull out a molecule, right? Here's my molecule, right, like this. Well, it sees a positive charge up here and a negative charge down here. And so the electrons get stretched the other way. The electrons get stretched with their positive part of their charge cloud this way and their negative charge. They can't leave the atom, but an electron can spend more time up here and leave a little more nucleus down here. And so it reverses the electric field of that's produced here. And so now, if there are a whole bunch, they kind of cancel each other out because there might be one that's here that's plus this way and minus this way, and these guys might cancel. But at the very top, you end up with a net negative charge at the top and a net positive charge at the bottom, of course, which add up to 0 because charges can't move in a dielectric, in an insulator. But this has the effect of mitigating the charge buildup here. And so when you're bringing another positive charge around here, it doesn't see as much of a repulsive positive charge, and so it increases the capacitance. And so if you have a that's supposed to be the Greek letter kappa. The capacitance becomes is increased by the factor of the dielectric constant. Kappa is unitless. So for example, one that comes up a lot is so if you slide neoprene rubber inside your capacitor, it increases the capacitance of the capacitor by a factor of 6.7, which is non-negligible, right? And so in the previous example, we said the capacitance, so what we got for the capacitance of that capacitor was 6.6 times 10 to the minus 7 farads, right? I'll call it C prime or something. Is equal to kappa times epsilon naught A over D, which is kappa times C, which is this guy, which is 6.7 times 6.6 times 10 to the minus 7 farads. Hopefully I'm still on screen there. I seem to be. So what I got for this was 4.4 times 10 to the minus 6 farads, or 4.4 microfarads. So dielectrics increase the capacitance of capacitors by a factor of their dielectric constant.